Thank you very much. Okay, thanks. So let me talk about the recurrence and transience of random walks on a bounded grid in increasing dimensions. I'm Shuji Kijima, and this is a joint work with Shuma Kumamoto. He's a PhD student, and he cannot come to here, and Tomoyuki Shiraki. Okay, this is the talk original plan of my talk, but I recognize that I need at least 49 minutes to talk all of them. So I skip some of them, which are very interesting topic, but I skip some of them. And so you can find this slide from my homepage, and just you Google search with my name, Shuji Kijima. Okay, let me start with the introduction with some examples. So recurrence and transience is a classical topic in the in the context of random walks on infinite graphs. So what is recurrent and transience? So a random walk on infinite graph is recurrent at vertex B if it visits B infinitely many times. So this is formulated in this equation. So this means that the sum of the probability that X returns to the vertex B diverges, then the random walk is said to be recurrent. And if it is not the case, the random walk is said to be transient. For instance, random walk on integer line, so starting from origin vertex, the random walk is recurrent at the origin vertex. And in the two-dimensional integer grid, random walk is also recurrent. It's not trivial, but a well-known fact. However, in the three-dimensional integer grid, random walk is transient, meaning that starting from the origin, the random walk returns to this vertex at most finitely many times. Then, so random walk, as I said, random walk on three-dimensional integer grid is transient. However, if it is trivial that if the region is restricted to the finite region, then clearly random walk is recurrent at the origin vertex. So the question is, a random walk on this region is recurrent or transient if n increases as time goes on? So answer is easy. It depends on the increasing speed. So we are interested in the phase transition point regarding the growing speed. That is the topic of this work. So let me explain the precise model of this work, random walk on growing graph. So firstly, growing graph is a sequence of static graphs, G equals G0, G1, G2, where each GT equals VT, ET is a normal simple graph. And in this talk, we assume that the vertex set grows monotonically, meaning that VT is included by VT plus 1. And similarly, we also assume that the edge set is also monotonically grows, so meaning that ET is included by ET plus 1. Then, random walk on growing graph is a specific model characterized by three tuple of function DGP. So D1, D2, D3 are positive integers denoting the duration time. Then growing graph is given by GT equal G of n for these time durations. This means that for the first D1 step, the shape of graph is G of 1. Then next D2 step, the shape of the graph is G2. And the next D3 step, the shape of graph is G3. That is the model of the random walk on growing graph. And let Pn denotes the transition matrix on Gn. So in this talk, I assume that the Pn is a simple random walk or lazy simple random walk on graph Gn. So let me explain an example of random walk on growing graph. So let D equal DGP be a random walk on growing graph where dn equal n square, and gn is a grid graph of described in this way. And let Pn denote the simple random walk with reflection bound, meaning that random walk move to a neighbor vertex with probability 1/6 unless boundary. So n square means that for the first step, random walk moves on this graph, and the next four steps, random walks moves on this on this graph, and next 9 steps, random walks moves on this graph. Then, concerning the growing speed dn, if the duration function dn satisfies this condition, then the random walk is recurrent. Otherwise, it is transient. This means that in this case, dn is n squared. So applying this theorem, so this value diverges. So this means that the random walk is recurrent. However, if we set dn equal n to the 1.39, then this value is converged, bounded at most 1,000. So it is transient. Okay, this is our problem. I have another interesting example, random walk on infinite canary tree. Random walk on infinite canary tree is transient at R at the root, starting from the, so we consider random walk on infinite canary tree starting from the root vertex. Then clearly, it's not clear, but it's almost clear that the random walk is transient at the root node. And this is clear, but random walk on a finite canary tree is recurrent at R. Then the question is the random walk on canary tree recurrent or transient if its height and increases as time goes on? The answer is it depends on the increased speed. And we can establish a similar threshold theorem, but due to the time limitation, let me skip this slide. Okay. So next, I'll talk about the related work about analysis of algorithms in dynamic environment. So analysis of algorithm, including the random walk on dynamic graph, attracts many attentions. So for example, concerning the graph search by random walk that is related to cover time, Cooper and Fries investigate the crawling on simple model of wave graphs. Arpin, Koki, and Lotka give a bad example for hitting time and cover time, which is exponential large to the number of vertex n. Denshiko and Rodriguez give an upper bound of cover time under some fairness condition, and Lampro, Martin, and Spirakis give an analysis of edge uniform stochastic graphs. Savelbardo and Zanetti give an order n square cover time for D regular graphs. And I, with Shimizu and Shiraga, propose the model of random walk on growing graph and investigated the cover ratio in this model. Concerning the mixing time, Saraf-Coste and Seniga gave significant result about the mixing time for time inhomogeneous Markov chain with an invariant stationary distribution. And Dembo and Chen give an analysis of the conductance of growing subregion of D-dimensional integer lattice. And Kai, Savelbardo, and Zanetti give some analysis of mixing time for edge Markovian graph model. And there are many other analysis of random walk on dynamic graphs. However, many of them are concerned with dynamic graph with a fixed vertex set. And only these 3 works are investigates the model where vertex set also grows. It's not invariant. And so let me briefly advertise our previous work. And in the work, we are concerned with collecting an increasing number of coupons. So suppose we draw a coupon every day, single coupon every day. And the first day, we have just unique coupon. So we have to draw this number 1. And day 2 and 3, we have two options. And we draw 1 from 2 uniformly at random. The next 3 days, we have 3 options, and we draw 1 from 3 uniformly at random. In the next 4 days, we draw 1 from 4 uniformly at random. Then the question is, how many types are corrected in the end of nth period? And order of n, order square root n, half of n, 99% of n, and I have not enough time, so I'm sorry, but I'm cheating. The answer is number 5. At least n-1 coupon we can correct in expectation. So meaning that except for 1, we cannot specify the one, but we can almost all we can correct almost all coupons. So in this growing speed, this is a formal description of this fact, but I can explain this proof in 5 minutes, but I have not enough time to, so I skip this slide. So coupon corrector is often regarded as a random walk on the complete graph. So we can extend the arguments to random walk on general graph. And if you're interested in, please refer to this work. Okay, let me go back to the related work again. So about the recurrence and transience of random walk. So in the context of recurrence and transience, so there are much work about the growing graph exist. In the so for example, in the so it is investigated in the context of self-interacting random walks, including line-forced random walks, excited random walks, etc., since 1990s or before. And closely related to our work, Denbo and Sidorov gave 2 papers in 2014. They are concerned with the growing subregion of d-dimensional integer grid, and they prove that the random walk is recurrent on the growing subregion is recurrent if and only if the sum of stationary distribution diverges. And so they prove it using the conductance argument, and there are several developments using the arguments heat kernel evolving set arguments. In another context, Amir Benjamin, Guergrevich, and Kozma give an proposal problem about the random walk on growing tree, and Fuan solves some conjecture, and where he gave analysis of the growing graph with uniformly bounded degrees. And this year we give 2 papers including this talk, and we are concerned with this specific model random walk on growing graph, and we give a phase transition point threshold of the growing speed concerning the K-Nari 301 hypercube or bounded grid with an increasing dimension. And our technique is path coupling. Our technique uses a coupling technique. So next, let me talk about this work about the recurrence and transience of random walk on growing graph for the purpose to introduce the basic technique and its issues. Okay, this is another example, random walk on hypercube with an increasing dimensions. So let DGP be a random walk on growing graph where dn equal to n, and gn is a 0,1 hypercube skeleton of n items. And let Bn denotes the simple random walk. So it means that random walk move to a neighbor with probability 1 over n. Then, so we can establish this theorem, and this theorem says that, so in this case, dn substituting dn here, then this value diverges, then this random walk is recurrent. So to prove this theorem, we introduced the notion of less homesick as graph growing, and we proved that random walk on the 0, 1 hypercube is LHAGG. And what is LHAGG? So this is the definition. So let D1 be a random walk on growing graph, and let D2 be another random walk on growing graph. And we say D1 is less homesick than D2 if the return probability of D1 is smaller than that of D2, where R1t and R2t respectively denote the return probabilities of D1 and D2 at time t. Then we say a random walk on growing graph D equal FGP is less homesick as graph growing, abbreviate LHAGG, if D is less homesick than D prime equal GGP for any G satisfying this condition. This means that D and D prime uses the same G and same graph G and transition matrix P. So this means that D and D prime grows similarly. But this condition means that D grows faster than D prime. So in summary, less homesick as graph growing means that the faster a graph grows, the smaller the return probability is. This is the definition of LHAGG. Then, under the condition of LHAGG, we can prove the following to sufficient condition of recurrence and sufficient condition of transient, respectively. And using these two theorems, once we obtain random walk is on hypercube is LHAGG, then we can establish this theorem. So here, let me explain the proof of this lemma. But before the proof, so I would like to answer the FAQ. So the faster graph grows, the smaller the return probability. It sounds trivial. So is there any, FAQ is that, is there any example which is not LHAGG? And this is an example. So we consider lazy random walk on this growing graph. So G1 is just a path. And G2, the pendant is appended to the root vertex. And G3, another pendant is attended to the root node. Then, as growing the graph, the return probability to the root increases. So this graph is not, this simple random walk on this graph is not LHAGG. So LHAGG is not a trivial property. Then let me prove the random walk on 0, 1 hypercube is LHAGG. The proof is essentially the monotone simple monotone coupling. So very, very simple. So let xt follows the df, and let yt follows dg, where we assume that dg grows faster than df. Then let xt and yt denote the number of ones in xt and yt, and here notice that the dimension of xt is always smaller than that of yt because dg grows faster than df. Then the transition probabilities of xt and yt is described in this way. Using this transition probability, we can couple xt, and if xt is smaller than yt, then we can couple so that xt plus 1 is smaller than yt plus 1. And similarly, if xt equal yt, then we can couple so that xt plus 1 is smaller by yt plus 1. This means that if yt equal visits the origin vertex, then xt is also visits the origin vertex, meaning that the probability that yt is visits origin vertex is smaller than that of xt. So we obtain the random walk is random walk on this 0, 1 hypercube is LHAGG. So it looks a very simple exercise if you are familiar with coupling, but the dimension of xt and yt is not the same. It causes some trouble in general. Okay. What's this? Oh, I see. Then, so this is one of the result of our previous work, and we obtain a random walk on 0, 1 hypercube. Then let me skip this slide, but so it is natural to think extend from 0, 1 hypercube to 0, 1, 2 boxes. And we consider to extend to 0, 1. So from binary to digits. Then in this talk, we are concerned with this problem. The target is random walk on bounded grid with an increasing dimension. And let D equal DGP be a random walk on growing graph where Dn equal n to the n, and Gn is a skeleton graph of this integer grid, and let Pn denote a lazy simple random walk with reflection bound, and move to the neighbor with 1 over 4n unless boundary. Then the question is the random walk on this graph LHAGG? Then the answer is we cannot prove it. Then instead we introduce a new notion of weakly LHAGG, and we establish this threshold. Okay, so what is a weakly LHAGG? So recall that this is the definition of LHAGG, and LHAGG means that the faster graph grows, the smaller the return probability is. Then in the weakly LHAGG, we replace this condition about the return probability with the condition of the sum of return probability. This means that the faster a graph grows, the smaller the expected number of returns is. So because the sum of return probability is equal to the expected number of returns. Then we assume a very natural assumption. That is, one is every transition matrix has a unique ergodic, meaning that unique stationary distribution. And the second condition is that every Markov chain is the mixing type of P is not very big. So this condition means so I don't explain the detail of this condition, but every rapidly mixing Markov chain satisfies this condition. So very weak condition. Then under these two conditions, and with assumption of weakly LHAGG, we obtain these two sufficient conditions of recurrence and transience. Here is a proof, and I can prove it in 5 minutes, but I have no more time, so let me skip it. Anyway, we obtain a sufficient conditions of transience, recurrence and transience. So the remaining task is to prove that random walk on this grid, finite grid, so bounded grid is weakly LHAGG. And as I said, we cannot simply apply the monotone coupling, and we developed the posing coupling. This is a picture of a posing coupling. So let X be a sequence of random walk X0, X1, X2, which follows DF. And let Y be a sequence of Y0, Y1, Y2 follows the DG, where the graph in DG grows faster than DF. Then we couple X and Y instead of XT and YT. So for this purpose, we define time correspondence TST depending on Y, so that if YT does self-loop, then so does X, corresponding X. Then if YT updates the ice coordinates, and it is possible for xi2, then we update x in the similar way. However, the dimension of y is usually greater than x. So there exists some impossible motion. In that case, we let x pause here. Then we have to do is to check measure conservation of the coupling. So this is the outline of the proof of the weakly LHAGG. And let eta denote the coupling described in the previous slide. And we have to prove two things. So one is that the coupling eta is valid, meaning that preserve the measure. And the second task is that the coupling eta preserves, I'm sorry, this is wrong, some partial order condition. Then we can prove that the number of return to the origin vertex by x is greater than that of y. This is the outline of the proof, but of course we know we don't have enough time. Let me skip the proof. Okay, let me conclude my talk. So I talk about the recurrence and transience of random walk on growing graph, and we give a sufficient condition of recurrence and transience under weakly LHAGG. And using the result, we prove that we give a threshold of growing speed of this model, and the proof we develop a proof technique of pausing coupling. So our future work is a simplification of the proof. So I like the idea of the pausing coupling, but the proof I feel is still messy, and we need to simplify the proof. And we want to extend to the technique to other random walk on growing graphs. For example, Galton-Watson tree or preferential attachment graph and more general graphs. We are also interested in the edge growing graph with edge dynamics, meaning a growing plus edge Markovia. Another future work is an analysis of random walk on growing graph beyond recurrence and transience. For example, hitting time, meeting time, gathering time, and so on. And I'm also interested in to find a new limit undefined for an infinite graph using this RWOGG model. Okay, that's it. Thank you very much.
Well, this slide for half an hour must be a record. We have some time for questions.
What we say this?
And anything else questions? Okay, everybody wants to go for lunch. Thank you very much.